In this video, we're going to provide some details about clustering. We are going to motivate why clustering is important, and then we're going to outline a very simple clustering method, which is called Kmeans. So let's start by the motivation of clustering. Clustering allows us to find and understand patterns in our data, and it's a type of unsupervised method that works without having any data labels. In this example, we see a clustering of the characteristics of the populations in Europe. And we see that if we cluster populations based on their characteristics, then the resulting clusters are the geographical locations of the boundaries in the countries of Europe. Also, another important reason of why we use clustering is to summarize our dataset and essentially reduce the size of large datasets by assigning a corresponding sample to its cluster. So clustering is effective when we do not have labels about our data, and therefore we have a less well-defined problem that results in no obvious error metrics. Applications that involve clustering in real life include topic modeling, for example, when we would like to cluster news articles based on their topics, market segmentation, or even clustering of images such as handwritten digits. And there are two important notions that are involved in any clustering algorithms: the notion of intra-cluster distance and inter-cluster distance. So essentially, we want our clusters to be as compact as possible. This means that the intra-cluster distance, meaning the distance within the samples that belong to each cluster, needs to be minimized. Here we see three quite compact clusters that are for which the intra-cluster distance is quite low. On the opposite side, the inter-cluster distance, which refers to the distances between the different clusters, needs to be maximized. And again, this results in compact clustering outcomes. The notion of clustering can be ambiguous. For example, if we see this sample of data here, it's not obvious whether 2 clusters are enough to categorize our data. 4 clusters are enough, such as clusters that are being indicated by this example here, or even 6 clusters. And the number of clusters can also be guided by the domain of interest and the problem that we are working for. Therefore, we need to have quite a good intuition about our data. We're going to discuss 2 different types of clustering in general in the next videos. One type is partitional clustering, and the other is hierarchical clustering. So partitional clustering works in that we do not assign any hierarchies in the clusters, and therefore from the original data points, we get different subsets of them, which are considered to be the clusters of our dataset. In contrast, for hierarchical clustering, we impose some type of hierarchy onto the clusters. So for example, in this case here, we have samples P2 and P3, which belong to one cluster by themselves. And then the combination of this cluster with sample P4 is considered another larger cluster of data. And here you also see the dendrogram structure of that hierarchical approach. Finally, our entire data set comprised of samples P1, P2, P3, and P4 is considered to be a cluster by itself, as denoted by this big circle here, and as denoted by this first layer of this dendrogram. Following that, we're going to discuss this and summarize some details for K-means clustering. So K-means clustering is probably the most widely known clustering approach, and it has a very simple and intuitive mechanism. Let's consider that we have an input data of any dimensionality, and our input data is being represented by samples x1 through xn. And we have a set of clusters, let's say K clusters, that again have the same dimensionality as the input data. The goal of K-means clustering is to assign a cluster membership to each of the samples. So at the end of the day, each sample should be assigned with a cluster membership function, A of xn, which is equal to 1 or to 1 up to k, where k is the actual number of final clusters. In order to learn our clusters, we need to formulate our problem via what we call a distortion metric. So a distortion metric goes back to the notion of inter and intra-class distance that we discussed in the previous slides. We want as much as possible to minimize the intra-class distance, meaning have as much compact clusters as possible, and maximize the inter-class distance, meaning each cluster should be as far as possible from each other. Therefore, what we are doing is that we are computing the distance of each sample to each of the cluster means, and then we are trying to find which assignment R and K is the one that minimizes this distortion metric. It is also important to note that this assignment R and K is either 0 or 1, and this refers to what we call a hard clustering approach. So R and K will be only 1 for a single cluster, and that will be the cluster to which sample N will be assigned. Otherwise, it will be 0 for all the other clusters. This is exactly what this equation says. So if the cluster membership for point xn equals to k, then R and K will be 1. And for all the other k, it will be 0. So for this distortion metric, the distance between only each sample and its assigned cluster is being taken into account in this sum. And this sum is a double sum that spans across the number of samples and across the number of clusters. So we would like to assign our points to clusters 1 through k, such that this distortion metric is being minimized. In order to do this, because obviously we cannot find a closed form solution, we will run an approximate algorithm. And the approximate algorithm that we will run has 2 important steps. As an initial step, we initialize the means of the clusters with some random values, and this is step number 0. So as the first important step, what we are doing is that we assign each data sample to the cluster whose mean is closest to that data sample. So we are computing the distance between each data sample and the mean of each cluster. And the cluster for which this distance is the minimum, this is the one that is being assigned to which sample xn is being assigned. And this is essentially what this equation is all about. So in step number 1, for each data sample, we are assigning each data sample to the cluster that has the closest mean to that data sample. For step number 2, what we are doing is that we are updating the means of our k clusters such that the means are the means of the data samples to which each cluster has been assigned. And we repeat this process as many times as we need until it converges. Here is a visual example of this process. Here is our initial data set, which is being represented by these green samples. And here, with these 2 blue and red axes, we have the initialization of the means of our clusters, mu1 and mu2. So as a step 1, we are assigning the samples that are closest to the blue center to the blue color, and the samples that are closest to the red center to the red color. As a step 2 now, we are revising the means of each of the two clusters based on the mean of the samples to which they were assigned. So essentially this blue X is being moved here because this is the mean of all these blue samples. And this red X is moved here because this is the mean of all the red samples. Now we have to repeat step 1 again, which means that using this mean, we are going to assign to this red cluster the samples that are closest to this mean. So this is the new assignment for the red samples. And in the same way, this is the new assignment for the blue samples. This process is repeated a couple of times until at the end we have this final assignment for which this is the blue cluster and this is the red cluster here. And of course, there are some limitations of K-means algorithm. One of these limitations is that there is no guarantee that the procedure terminates at a global optimum. Basically, we are having a greedy optimization procedure for which each time we assign each sample to its closest mean. In order to avoid any local optima, we can restart our algorithm multiple times. So this is an example of how the algorithm for different initializations can have different results. Here we see our original points, and here we see one example of clustering, while in the bottom right we see another example of clustering. Clearly, the example on the bottom left is much better compared to the bottom right, but again, it depends on the different initialization that we have for K-means. Some other solutions in order to avoid this local optima, this challenge with local optima, is to first start with her hierarchical clustering approach in order to determine the initial centroids and then go to K-means. Or another solution is to choose more than K initial centroids and then just select these that make more sense after running the K-means algorithm. When to know how to stop is an important thing when it comes to K-means. So a rule of thumb here is that we are trying to stop when the distortion metric is becomes quite stable. So we keep running this iterative procedure, and in this plot, in the x-axis we have the K-means iteration, in the y-axis we have the distortion metric. Obviously, the distortion metric decreases the more we run K-means. So we choose to stop running K-means when the decrease in error becomes almost flat. And this method is also referred to as elbow method, again, because we are running K-means until we see an elbow. And when we find this elbow, we stop. Another application which is important for K-means and for other clustering approaches is what we call vector quantization. So if we would like to compress our data set, instead of keeping all the original values for our data, we can perform K-means clustering. And then after having a set of known centroids, we can replace our data points with the corresponding centroid. This saves space because instead of having all the values for all dimensions for a single sample, we can just have an index for a single sample that points out to the centroid to which this sample belongs to. Of course, this compression is lossy because we cannot go back and fully reconstruct our data, but in certain cases it can work. And this is an example on how this compression can work, let's say for this original image. So for this original image, we have applied K-means with 25 centroids, 10 centroids, and 3 centroids. So we see here that, of course, with 25 centroids, we keep more information. And we see that, for example, these red pixel values are replaced by a single red color in contrast to what had been there. And we also see, for example, that these kind of brownish values here are replaced by a single brown color. Of course, as we discussed, with K-means there are several limitations. one of the limitations is that the clusters might be of different size or of different density. We might have some clusters that contain more samples than others. Another major limitation in K-means is that the clusters, especially if we use Euclidean distance, reflect spherical shapes. So there's no flexibility to have non-spherical cluster shapes involved, which is something that, as we will see with Gaussian mixer model, there is more flexibility. Also, K-means are obviously sensitive to outliers because it's a hard thresholding, a hard assignment algorithm. If there is an outlier data sample, it has to be assigned to a specific cluster. So it will subsequently affect the mean of that specific centroid. And finally, as part of K-means, it is hard to determine the optimal number of clusters, which is something that can be, of course, done by, can be improved by actually having some domain knowledge about our application. So this is the end of the video that describes the K-means algorithm. In the next video, we're going to see what we call a soft generalization of K-means, which is referred to Gaussian mixture models algorithm.